Now, let us see the modern periodic law or Mosley periodic law. Mosley proposed atomic number to the element. Atomic number is a best property to explain the properties of elements rather than atomic weights. If you know the atomic number, you can write the electronic configuration. If you write the electronic configuration properly, you can know the valence shell and valence electrons. You know valence electrons are the cause for the chemical properties or physical properties. That is the reason physical properties and chemical properties are dependent on atomic numbers or electronic configuration. So, this was proposed. It is called, this law is modified. Mendeleev periodic law was modified as modern periodic law or Mosley periodic law like this. Physical and chemical properties of elements or periodic functions of their atomic numbers or electronic configuration. So, Mosley periodic law or modern periodic law. Modern periodic law or Mosley periodic law is dependent on atomic numbers or electronic configuration. On the basis of this law, elements were again arranged in the form of a table. The table is called modern periodic table. It is also called as long form of the periodic table, because in Mendeleev periodic table only 8 groups or 9 groups are there, whereas here 18 groups are there, 18 vertical columns are there. So, it is called long form of the periodic table, which contains 18 groups, long form of the periodic table, or it is also called as a Bohr's periodic table or Bohr-Thomson periodic table, because the electrons enters in the orbits. Each period indicates one orbit. That is the reason the outer orbit number period is indicated by the outer orbit number. That is the reason the orbits were proposed by Bohr and Bohr-Thomson, we can say, model. Hence, this law or this table is also called as Bohr's periodic table or Bohr-Thomson periodic table. Bohr-Thomson periodic table. In addition to that, the electrons of each electron, differentiating electron, that means last electron entering in the orbital, that it simply follows the electronic configuration. Electronic configuration is followed by Aufbau principle. Hence, this table, if you see this table, as it is dependent on the electronic configuration and it follows the electronic configuration, so we can say it is also, this table is also following the Aufbau principle. In the Aufbau order, the elements are situated or arranged. Next one, let us see salient features of the atomic model, that is, modern periodic table or long form the periodic table. Here, what are the features of this main table, long form the table? It contains 18 groups, 18 vertical columns, and 7 periods. The successive element differ 1 unit of atomic number. First element, the atomic number 1, next comes 2, 3, 4 atomic numbers. Every 2 successive elements differ only 1 unit of atomic number. How many groups are there? 18 groups are there. How they are arranged? The groups, subgroups of the Mendeleev periodic table. In this table, first A, second A, next comes third B, fourth B, fifth B, sixth B, seventh B, eighth, 3 groups. These elements are called iron, cobalt, nickel, ruthenium, rhodium, palladium, osmium, iridium, platinum. These are called transition triads. Next comes first B, second B, first B and second B. After this is copper group, copper, silver, gold. These are called coinage metals. First B contains copper, silver, gold, which are used for coins, preparation of synthesis of coins. So, they are called coinage metals, copper, silver, gold, and zinc, cadmium, mercury. These are called zinc group, second B. Afterwards again comes A subgroup, first A, second A, third A, fourth A, fifth A, sixth A, seventh A, and zero group. Zero group elements are there. So total 18 groups are there. The groups are numbered from 1 to 18 as per IUPAC system. So you should calculate like this. Suppose third A group is now according to IUPAC system, it is 13 group. Fourth A group according to IUPAC system you have to call is 14 group. 14 group. Zero group is called as according to IUPAC system 18th group. So remember 1 to 18 groups are numbered as per the IUPAC system. What are the periods? First period contains two elements. Periods, the horizontal row is called periods. First period hydrogen and helium. Two elements are there. It is called shortest period, which contains two elements. Second and third periods contain 8 elements each. Second and third period is 2 and 6 here. 8 elements each, so they are called short periods. And fourth, fifth periods are called, fourth and fifth periods are called long periods, which contains 18 elements. Here fourth period, this 10 D black elements, 2 S black, and this is P black, you can say. Total, these are 6, total 2 plus 10 plus 6, total 18 elements will be there. Sixth period contains 32 elements, which is called longest period. In sixth period, here 2 elements S black, D black elements 10, and P black elements 6, and here after third A, this lanthanides, after lanthanum here, lanthanides 14 is also there in the sixth period. Lanthanides belongs to sixth period. So sixth period contains 18 plus this 14 F black 14 groups. 14 total 32 elements will be there in the sixth period, which is called longest period. Sometimes longest period contains how many elements? You will ask in the general entrance. Longest period contains 32 elements. Most of the students think because long form period table contains 18 groups, so 18 elements may be there, but 18 is not correct. Here the lanthanides also comes in sixth period. So these 14 and these 18, total 32 elements will be present in the long form of the period table. Seventh period is incomplete period. So the other chemicals are other elements are will be discovered, and their properties will be studied. Afterwards they will be kept here. So nowadays 118 up to 118 element were temporarily identified, and they were kept in the this table. Next, each period starts with the alkali metal and ends with the zero group. Every period hydrogen, helium. Similar like that. NS1, hydrogen 1s1, lithium 2s1, this one 3s1, 4s1, 5s1, 6s1, like that. So the period number indicates principal quantum number, primary quantum number, that is principal quantum number, Bohr's quantum number will be known by seeing the period number. Suppose this element, if you want, 4s1 is the outer shell configuration, 4s2 is this s2, 4s afterwards 3d, because of our principle 4s, after filling the 4s, 3d will be the orbital subshell will be filled by the electron. So 3d1, 3d2, 3d3, like that, 3d10, 4p again, 4p1, 4p2, 4p3, like that, 4p6. So every period starts with the S1 and ends with the S2p6, S2p6 except helium, So every period starts with the NS1, S1 generally you can say 1s1, 2s1, 3s1. In general you will write NS1 configuration of alkali metals, and NS2 NP6 configuration of inert gases comes under when the period starting and ending points, ending elements. Starting element is NS1 and ending element is NS2 NP6. So each period starts with alkali metal. These are alkali metals. First period start except hydrogen. Second period lithium, alkali metal. Third period sodium, potassium, rubidium, cesium, francium. All are alkali metal. Starts with alkali metal and ends with the inert gases. Helium is S black. Actually, this is 1s2 configuration. It should be here, but due to similar properties of inert gases, completion of the orbital, outer orbital, so it is kept here in inert gas group. Helium is a S black element which is present in the P black. Afterwards I will tell. Hydrogen, helium, neon, argon, krypton, xenon, radon. These have configuration, general configuration NS2, NP6. So each period starts with alkali metal except the first period and ends with the inert gas. Ends with the inert gas. Inert gas it ends. That is the reason. Next, what we will see? Let us see the groups. Groups are vertical columns are called groups. Here, based on the differentiating electron. Differentiating electron means last electron enters in the subshell. So it differentiates this element with the next element or this element with the previous element. So for example, 1s1. Next electron comes next element 2. So differentiating electron means last electron which enters in the subshell that that indicates the element belongs to which black. For example, so on the differentiating electron, the elements were classified into the periodic table of elements classified into 4 blacks. They are called S, P, D, and F. Blacks. Black means a piece. Blacks. S, P, D, F blacks. This classification is dependent on the differentiating electron. The last electron enters in which subshell. Suppose last electron enters in the S subshell, that element belongs to S black. If it enters in the P subshell, valence shell, then P valence subshell, then it is belonging to P black. If it enters the n-1 D shell, that means penultimate D subshell, then it belongs to D black. If it enters the last electron, that is called differentiating electron enters in the n-2 F, that means n ultimate, n-1 is penultimate, n-2 is equal to is anti-penultimate, anti-F orbital of anti-penultimate shell, then that element belongs to F black. So in this way, these can be classified. This may become in the form of an essay question to the intermediate students, and you will get so many bits from this classification. In S black, for example, first classification is S black. In S black, differentiating electron enters in S subshell. So S1, S2, S1 and S2. This green is a S black, S1. 1s1, 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. The second A, 1s2, but it is kept in the, although it is S black element helium, it is kept in P black because it is similar, it has similar properties to the inert gases. So an element of S black which is kept in the P black is helium. Remember, helium, that may come in the entrance bit. First A, NS1 configuration, those are called alkali metals, hydrogen, except hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. Second A is called alkaline earth metals. Their outermost shell electron configuration is ns2. The last electron enters in the s2. S orbital is completed. S orbital is completion takes place in s subshell. So this is 2s2, 3s2, the beryllium, calcium, strontium, barium, radium. So these are ns2 configuration. These are called alkaline earth metals. These two groups comes in S black. Alkali metals having ns1 configuration, and alkaline earth metals having ns2 configuration comes into this black. This classification in this black, the differentiating electron enters in the s subshell. As s subshell consists two electrons, it consists two groups, 1, 2, 1s1, 1s2, 2s1, 2s2. Only two groups will be there in the S black. Next, P black. Let us see. It consists two groups, 14 elements. These are 7 elements, and these are also 7 elements. This element also comes here. 14 elements. S black consists two groups and 14 elements. Their general configuration can be written as ns1 and ns2. So ns1 to 2. ns1 to 2 is S black element, but placed in P black. Helium, sorry, it is not he. Helium is a S black element, but placed in P black, that is in inert gases. Although helium should be kept here in the alkaline earth metal, but its properties is similar to the inert gases, so it was kept in zero group. P black. In P black elements, differentiating electron in NP subshell. NP subshell. Last P subshell it is kept in the P subshell. P subshell consists 6 electrons. P1, P2, P3, P4, P5, P6. So P1, this is boron family. NS2 NP1 you can write. Next comes NS2 NP2. This is carbon family. Carbon, silicon, germanium, tin, lead, and next comes nitrogen. Nitrogen family is also called natcogen. Nitrogen, phosphorus, arsenic, antimony, bismuth. Next comes oxygen family. Oxygen family are called chalcogens. Chalcogens means mineral producing element. So it is chalcogen. Oxygen family you can write. Oxygen NH2 NP4. NH2 NP3 is the nitrogen. NH2 NP3 general configuration. For oxygen family, NH2 NP4. Oxygen, sulfur, selenium, tellurium, polonium. Next, halogens. Halos means salt producing agents. Genus means producing agents. Salt producers. So these are fluorine, chlorine, bromine, iodine, astatine. These are all called halogens. Their configuration, general configuration you can write for halogens, NH2 NP5. Next, helium, except helium, neon, argon, krypton, xenon, radon. These elements are called inert gases, because inert, they are completely filled s and p orbitals of the outer shells, so they do not share, do not contribute electrons, so they are inert in nature. They don't react with other elements, so they are inert in nature. So they are called, these are all are gases, so these are called inert gases. This is about S black, you can write. In S black, another peculiarity is there. In S black, these elements here in margin elements, these are metalloids. These are gases. These are you can say non-metals. This part is metals. The part is semi-metals or metalloids. This diagram, elements connecting the diagram of this. These elements are having both metallic and non-metallic nature. Those are called metalloids. You can know boron, silicon, and here germanium, germanium and polonium, astatine. These are all comes under the metalloid nature. These are non-metals. Here you see these are non-metals. These are metals. These which are comes on in this diagonal area, those elements are metalloids or semi-metals, not complete metals. Semi means partial of metal, semi-metals. So all type of elements will be there in a P black. That is the special nature of the P black. So now, so the general configuration, let us see. General configuration is NS2 NP126. Here see, in P black elements, the differentiating electron enters in N subshell. Enters here, enters in a NP subshell. So they contain 6 groups called boron family, NH2NP1, carbon family, NH2NP2, nitrogen family, NH2NP3, which are called natcogens, and oxygen family, chalcogens. They are oxygen producing element. So NH2 elements, NH2NP4 halogens, salt producing elements, NH2NP5, and inert gases, NH2NP6. The general configuration is all contains NH2 P12 P6. So P12 P6. So what is the general electronic configuration for P black? NH2 NP126. This is about P black. So already here P black written there because of the lack of space in that slide. Here these are the gases, these are metals, non-metals, metals, these are metalloids. So metalloids: boron, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine. These are all 8 elements are there, metalloids. Mostly polonium is radioactive. These are called, remaining 7 are mostly in books 7 elements will be known as metalloids. Metalloids means semi-metals. Here you see all type of elements, say metals, non-metals, metalloids, inert gases are present in P black. Total P black elements are 35. 35 newly discovered these elements, including these elements. These are 30 newly recently discovered these elements in P black. These elements are also comes under the P black. So 35 presently 35 P black elements are there. Helium will not be in P black. You should not consider this element helium should not consider the P black. It is a black element. D black elements. In these elements, differentiating electron enters in N-1 d subshell. N-1 d subshell. Their general electron configuration is NS1 to 2, N-1 d1 to 10. For example, in the periodic table, long form of the periodic table, if you see, fourth period, 4s1, 4s2, next comes element scandium 3d1, not 4d1. According to the above principle, after completion of the 4s, which subshell will be filled with the differentiating electron, last electron? 3d. So 3d, this is called 3d series. 3d series present in 4th period. In 5th period, deep area, the red area, this is 5s1, 5s2, this is 4d1 to 4d10. In 6th period, 5d1 to 5d10. In 7th period, 6d1 to 6d10. Now these are also partially identified. So these total 40 elements are there in this one. Here the electrons are filled in N-1 d subshell. N-1 d subshell. Let us see. In these elements, a differentiating electron enters in N-1 d subshell. Their general electron configuration is NS1 to 2, N-1 d1 to 10. Why NS1 to 2? Because in copper, what is the electronic configuration of copper? you know in the atomic structure 4s2 3d9. No, generally it should be 4s2 3d9. Due to complete d orbital, completely filled d orbitals gives stability, one of the s electron goes to the 4s2 3d subshell. That's the reason the electron configuration is 4s1 3d10. So sometimes in copper group elements have s1, although they are belong to d black. That's the reason sometimes 1, sometimes 2, mostly 2 will be there, ns2 n-1 d 1 to 10, but in copper group 1 also appears. That's the reason in generally we can write the configuration, electron configuration for d black elements. D black elements ns 1 to 2 n-1 d into d 1 to 10. This is mostly in bits it will be asked. What is general electron configuration of d black elements? ns 1 to 2 n-1 into d 1 to 10. Why 1 to 2? Because in some d black elements like copper, silver, gold, instead of ns2, one of the electron goes into d subshell, so 1 will be appeared. That is the reason in generally this configuration can be written like this: ns 1 to 2 n-1 d 1 to 10. It contains 10 groups. They are third B, in the previous table, third B, fourth B, fifth B, sixth B, seventh B, eighth, 3 groups. Next comes first B and second B. Next comes first B and second B. All are metals. The d black elements all d black elements are metals. Remember, all d black elements except third B group, zinc group, second B group, zinc group, are called transition elements. Except the last group 3d9 up to 3d9, up to n-1 d9, the elements are ns 1 to 2, n-1 d 1 to not 10. It should not be completely filled d orbitals. For transition elements, outer d subshell should not be filled. D subshell partially to be filled. Such elements only considered as transition elements. As zinc group has 3d10, 4d10, 5d10. So except zinc group, the remaining elements of d black elements are called transition elements. Their general electron configuration also the same: ns 1 to 2, n-1 d 1 to 10. Why 1 to 9? It is not 1 to 9 because in copper group, zinc group, the previous to the zinc group, copper group is there. That is the first B group. First B group, actual configuration should be 4s2 3d9, but in actual case 4s1 3d10. So although it is 9 becomes 10. One of the electrons shifts from the ns level to n-1 d subshell. That is the reason ns 1 to 2, n-1 d 1 to 10 can also be written as a general configuration, general outermost electron configuration for transition elements, because they consist in 1, 2, 3, 4. So 4 periods. Each period contains 3d series 10, 4d series 10, 5d series 10, 6d series 10. So total 40 elements. 4 periods into 10 elements, 40 elements will be there in the d black